All right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Hopefully you guys are doing well this weekend. I guess, instead of jumping into it, which we will soon, I guess I just wanted to make a few comments on the project because I've been meeting with a couple groups in office hours over this week, and just there were some things that I was repeatedly saying, like people didn't really understand what it meant to approach the project with statistics. And I'm talking about Project 2 specifically. And by the way, a lot of you chose Project 2, and I'm not sure if you guys chose it just because I gave extra credit for doing it. You're like, oh my God, extra credit, and you're all just like all about extra credit. So Project 2 is actually like harder. You know that, right? Like I gave extra credit for a reason. It wasn't just like, it's a harder project to do. So yeah, you would have to be, I think, a lot better at programming. Even if you're using Excel, you are going to need some sort of programming skills to get through Project 2. Less so than you would Project 1, I think. I think just your basic run-of-the-mill Excel skills can get you through Project 1 if you do it correctly. But Project 2 is a little bit more challenging. And using statistics to make decisions, it comes down to you just analyzing a lot of data. So I want you guys to, you're supposed to be looking at the 2019 season or whatever season ended in 2019. It probably started in 2018, depending on what league you're looking at. And the thing is, I want you guys to pretend as if 2019 hasn't happened yet, right? So I know we have the data, it happened, but I don't want you to use that data until the end to kind of check how your strategies worked out. So when you're doing the statistics to actually make decisions, this will be made based on prior data. So you would look at the 2018 season, 2017 season, 2016 season, right? And understand that if you're doing the Premier League example that I gave on the project, that's about 380 games in a season. So that's a lot of data with a lot of players. And you can run that over 3 years, 5 years if you want to. Python or Excel won't care either way very much. And you can collect statistics to test what your strategies are. So you guys as a group could come up with a bunch of strategies, 10 say, and you guys can just use statistics to decide what are the most important things, right? And how you would actually do that is you would build teams based on each strategy, just one strategy at a time, just isolate each strategy. So you can say, I forgot what I mentioned before, like the people who scored the most goals over the past 3 seasons, for example, or the goalies with the most saves over the past 3 seasons, or anything of that sort. So what you can do is you can have all this data with all the players and all their stats, because you'll have a lot of stats for this sports. Everyone has a lot of stats for sports, right? And you can tell Python or Excel to sort the data, split it up into goalies and midfielders and forwards and blah, 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 and then sort them based on some criteria. So sort them based on the number of goals from in a descending order or something like that. And then you can tell it randomly pick people from a certain region and create a team for me as long as we are below budget. So you can tell Python or Excel to do that. Now, of course, to tell them to do that would require some programming. But basically what you would do is you'd build a team. So you might decide, you know what, I am going to build a team where this is experience is the most thing, the players who have been playing the longest. And so you organize by how long they're played. And so you pick a goalie who's the most senior, you pick a forward who's the most senior, you pick a midfielder who's the most senior, and you build an entire team of seniors, essentially, right? And you would come up with another strategy. Okay, whether they're playing at home or away. And so you'll pick a team where they're based on who's always playing at home, right? And that's a team. Your team is the guys who are always playing at home versus the team of seniors. And then you can do a bunch of statistics on this. How did these teams do over the past 3 seasons? You can come up with a bunch of numbers. And I would say for each strategy, you can build like 30 teams to have a good kind of statistical foundation. You'll need like 20 or 30 teams of all these 11 people with all their statistics. And it sounds like a lot, and it is a lot for a human being to do. It's not a lot for Excel or Python. And so, yeah, you can build 30 different teams at random. Tell Python to just pick according to this criteria at random, as long as I'm below budget. Build 30 teams with one single strategy. Follow their scores. Have Python teach Python how to score them based on the league rules, and score them at the end. And then you can see all the scores. You can see for each strategy, what were the statistics for the scores? What was the average score? What was the highest possible score? What was the lowest possible score? What was the variance in the score? What was the range? How confident am I that the scores they will get will be very close to the average, so I can predict it very well? Or maybe it was a widespread. Maybe, yeah, I know the average score, but it could be much better than that or much worse than that. I can't really predict it very well. And so you're gonna, after testing all these 10 strategies over like 30 teams per strategy, then you're going to start to, the statistics are going to start to speak to you. You're going to start to see, oh, certain teams get a higher average score, less variability. You can predict how well they're going to do better. And at the end of the day, you pitting these strategies against each other, you're going to start to see, it's probably more important to pick the seniors than it is to pick whether they're playing at home or away, right? Like the data will tell you, right? You'll see how their average scores pan out. And that's how you're going to build your team. After you do that statistical analysis, now you know in your mind what the most important things are to pay attention to. So we're not going to pay attention to these 10 things. We're only going to pay attention to these 2 or 3 things. And we're going to build a team based on these 2 or 3 things. And you're going to build that team. Less random this time. You can go in and you can scrutinize all the records and pick a guy that you think really exemplifies the strategies that you want to employ. And then afterwards, you look at the 2019 data for that team and you score it. And that's what you're going to measure it against. So that would probably be how I would go about it. So if you're at the beginning of the 2019 season, you're not going to know what happens in 2019. You're going to make decisions based on what happened prior, right? That's how we make decisions. Yeah, so I just sort of thought I would just talk about that because it seems like a lot of the teams that picked Project 2 just kind of weren't sure about how to go about it. So I think that's a good way to go about it. And of course, what I just said, you can tweak it a little bit for whatever reason. Like we decided to do this because of this reason. And you guys can just look up, or whoever you designate in the group to be the researcher can just look up how is statistic analysis actually done? Like, what is it that I'm supposed to, what is the kind of information that we're supposed to be gathering? How many data points do we need to be to make our statistics a little bit valid, right? So, I mean, I told you 20 or 30, which is good enough, but why was it 20 or 30? Right? This is something that you should know. You shouldn't just take my word for it. It's 20 or 30. Why is it 20 or 30? And you guys could look it up and just be like, you know what? I'm more comfortable doing 30 than 20 for this particular project for this particular reason, because the research says if I'm doing this kind of thing with sports statistics, it's better to do that. Right? You'll do your research. Yeah. So I thought I would mention that. And Peter, were you raising your hand or?
Yeah, I had a question.
Yeah. What's up?
Oh, geez, now I forgot. My question was, when we're choosing or when we're picking our teams and using those strategies that you were talking about, could we apply them instead of like just to one team at a time? Apply them to like defensive players, midfielders, and offensive players, like figure out what we think is the most effective strategy. For example, for goalies, we would pick them based on goals conceded, least amount of goals conceded, and then offenders, most goals scored, and then say for defenders, their influence.
Yeah, you can definitely do that. But if you're doing that, it'll take a little bit more work on your part because you would have to have some sort of control variable, right? So let's say you have 3 different criteria that you want to judge goalies by, and then you have 3 different criteria that you want to judge forwards by, right? You can't just randomly mix and match them, right? So you have to choose, okay, here's one strategy that I want to judge forwards by, and you have to run through all 3 strategies with the goalies. You know what I mean? Like if I have this kind of forward with this kind of goalie, how does it do? With this kind of goalie, how does it do? With this kind of goalie, how does it do? And then you have to go to the second strategy for forwards. Okay, with this kind of goalie, how would it do? Right? You, like once you start mixing and matching, building a team that incorporates multiple strategies, then you kind of have to know how those strategies would relate to each other within a team, as well as how that entire team structure would be built. You know what I mean?
Okay.
So you'd have to stratify it a little bit more within a team if you're doing that, which I think could work. But then I think on top of the 30 teams, you would kind of need a bunch of different combinations within them also.
Okay. You talked about code that could handle analyzing that much data, and we found some, but it only, like when we were running it, it could only handle, for example, analyzing like just the goals scored in the 2017 season. It couldn't handle like an entire year's worth. So we would end up having to run it like thousands of times in order to get the data, 30 teams worth of data. So we were wondering, I guess, maybe where would you find code that could handle running that many, like that much, that could handle that much data?
I mean, as in, you're just saying that it ran out of space, like, or it just ran out of runtime, like it couldn't process all that data all at once?
I think so. John, do you want to help me
Because,
out? Like
yeah, I would probably maybe talk to me in office hours, but I think what you could do is just combine the data for all the years into like one big table and just have it do analysis with that one big table. Right. As opposed, like if you leave all the tables separate, then yeah, you're gonna have to run the code each time for each year, which you may or may not want to do. But yeah, I don't think you're going to be anywhere near enough data that your program can't handle it. I just think it's how you organize it. Right? I mean, we use these things to run millions of billions of items of data every day. It's not going to sweat you doing 3 years of a fantasy league, really. So that shouldn't be an issue. It's probably just how you have the tables. Maybe they're in separate locations, they're separate files, so you'd end up having to run a different program, rerun the program for each. So that's the only thing I can see here. Like you shouldn't have a trouble with, it's too much data, can't do it, Captain. Like it's not going to happen. It's too much data. Okay, let's actually. Can't do it. Get down. Too much data. The chopper. Okay. Anyway, let's get into it. And yeah, once you have an idea of how you want to approach it, yeah, you can look up code to do each thing. You can have a code that will do most of the things you want to do, but then you have to look up separately a code that will do some extra thing that you want to test. Yeah, like 80% of programming is looking up what someone else did. That's what it is. You know, that's what they don't show you in the movies with all these hackers that are hacking into like these huge systems. Really, what they're doing is they're searching Google the whole time and just trying to figure things out. Maybe calling the front desk on the phone, pretending to be someone else to get into a certain system or whatever. All right, let's actually jump into it. Last time, we spoke about conditional probability. We also spoke about independence and mutually exclusive events. So conditional probability was that formula, probability of A given B. This is if you know an event B has occurred and you want the probability that an event A will occur, given that you know B has occurred. That's this probability. It's called conditional probability. It's very important. Two events are independent if one has no influence over the other. What this means is that, for example, if A and B are independent, knowing that B has occurred does not affect the chances that A will occur at all. And so the probability of A given B is probability of A, which tells you that the probability of AND is the product of the probabilities for independent events, not in general, for independent events. So we have these things, and those things are things that you definitely should know. Mutually exclusive means that they cannot occur together. One occurring excludes the other from occurring. So both occurring, chances are zero. Probably is zero that both of these things will occur. And ultimately that leads to this thing. When you kind of take the law of disjunction into play, or you can also use Axiom 3 from probability. So those were the important things, mutually exclusive. And we did an example of that to show that something is independent versus not comes down to you showing that these examples hold or don't hold respectively, and showing that something is mutually exclusive or not comes down to you showing that the mutually exclusive equations hold or do not hold respectively. So me asking, are they independent? And you sort of telling me, well, I feel like they're independent because this shouldn't affect that. Like, you're not going to get any credit for that. You need to show me the equation, the numbers. And maybe a little bit later, we'll actually see examples where this is going to, you're going to see why this matters, why you trying to reason through something with your intuition. It doesn't work. It's not something you can depend on, right? You have to guide yourself with the equations. I left you guys with an example here. And that's what we're going to do, which I added to probability set 1, which I encourage you to do the examples that we haven't gone through. And so that's what brings us here. So did anyone do it? What was the guess here for this?
Is it 0.2 or 20%?
0.2 is the final answer. Okay. Let us see. Maybe you can tell me how you actually did it. Let me make sure
Well, I made a tree diagram first.
All right, tell me how you did it.
Well, the first branch is male and female, 40 and 60%.
Okay, so this is male, 40%, and female, which I think the problem spoke about males, so we should probably think of that as male complement. I'm not really saying that, women are just there to complement. That's not what I'm saying.
Well,
I'm saying mathematically. What I'm saying is mathematically, if the problem talks about male, you probably want to write everything in terms of male just to make the numbers easier and you can see it easier. But okay, yeah. Then?
And then it says of the men, so given a man 50% smoke, so I branched off 50 and then obviously 50 non-smoker.
Male smokers, okay, so that's 50%, and male non-smokers, 50%. Okay.
And then I did the same for not male.
Yeah, not male. Whatever you want to be, as long as you're not male. So this is not male, or non-male smokers, like not male. Non-male smokers. That was 20%, yeah?
Yeah.
And non-male non-smokers. And this was 80%. Okay, all right. And what do you want to do? What did you do here?
I applied the conditional probability formula.
Oh, so what did you want?
I wanted, well, it says it wants a smoker is male. So wouldn't
Okay.
that be the intersection between smokers and males?
No.
No.
Yeah, no. So is that what you did?
Yeah.
So you did the 50% times the 40%.
Yeah.
Right. If that was what the question was asking, that would be correct, but it's actually not. Reading this question, can anyone tell me what I actually want? Like the problem didn't say, what's the probability that we choose someone and they're a male smoker? It's not what it says. What did it say? It says we chose from the smokers, and then afterwards we check if they're male, right? Suppose a smoker is chosen at random. What is the probability that the smoker is male? So what this is actually a conditional probability. The event of them being a smoker has already occurred, we shall say. And now I want to look at the event that they are male. So what we actually want is the probability that given that someone is a smoker, what is the probability that they're male? That's what we actually want. So let's and again, it's always good to define some variables here. Let M equals event person is male. Let S be the event person is a smoker, right? So what we have here is we have here the event M, and here we have the event M complement. Now over here, what we have is that given that we're on the M branch, what is the probability that they're a smoker? And over here, we're like, given that we came from the M branch, what is the probability that they're not a smoker? And over here, given that we were on the non-male branch, what is the probability that they're a smoker? And over here is given that we're on the non-male branch, what is the probability that they're not a smoker? Right, so these are the events. Which you can actually think of that as and, by the way, right? So you will notice that this guy, so I told you in class last time that if you multiply along an arm, it's almost like you're taking an and. And that actually makes sense with our formulas, right? Because if you look at, say, the probability of S given M, that is the probability of S and M over the probability of M. And so if you multiply the probability of S given M by the probability of M, that actually gives you the intersection. That gives you the and, right? So this is why multiplying along an arm and, right? Well, I told you that before, but now you kind of see why it had to work out that way. So now realize what you want. So what we know now is that the probability of M given S is the probability of the intersection of M and S divided by the probability of S, right? Now, what is the probability of the intersection of M and S? Well, it's going to be the 40% times the 50%. Now, what is the probability that they're a smoker? Looking at this tree diagram, how do I get all the smokers? What you can notice is that if I'm looking at the smokers, well, that could be the male ones, or it could be the non-male ones, right? Now, of course, these are non-overlapping things. These are disjoint sets, right? You're male or not male, which means Axiom 3 of the probability says we can add the chances. So we're pretty much going to add up the chances of going along the M arm versus going along the M complement arm. So that's going to be 40% times the 50% plus the 60% times the 80%. Sorry, I did. I covered the non-smoking arm. The smokers are here. Okay, so that's 60% times 20%. Okay, so that is the probability. So first you have to know what you're looking for based on the problem. You should recognize that it didn't ask you about an and. It asked you about, oh, we know people fall in this category. What is the probability that they also fall in this category, right? If we know someone is a smoker, the smoking event already happened. What is the probability that that smoker is a male? It's a very different kind of probability. It's a conditional probability. We want the probability of someone being a male. Given the condition, we know that they're already a smoker. And I believe that this comes out to 0.625. There's a 62.5% chance that if you pick a random smoker in this city, in Newport City, that you will pick a male. Right? So if you group all the smokers together and then randomly choose among only the smokers, the probability that you get a male is going to be 62.5%. We can also just do some of this. Note, you can write this below. We were given, or we are given, we were told the probability of being a male. The probability of not being a male would follow nicely. We're told, yeah, so that's 40% and 60%. Of the men, 50% smoke. So we're told, given that someone is a man, what is the probability that they smoke? 50%. Which means that given that someone is a man, what is the probability that they don't smoke would also be 50% because it has to add up to 100. We also know that given that someone is not male, what is the probability that they smoke? That is 20%, which means that the probability, if you're not male, the probability that you don't smoke is going to be 80%. Right? So these are the things that we're given, and you should recognize that those are the things you're given. And so it turns out, when you know that M and S, the probability of M and S is actually just the product of these two, you realize that, oh, I just have to multiply these two to get the M and S. And then when you realize the probability of being a smoker really means you are male and a smoker, or you are not male and a smoker, and you add up those two. Right? So you can do it that way. Now, it turns out that there's a nice formula for this, and that's what I'm going to derive for you in a little bit later. But first, so you can do this based on a tree diagram, but there is actually a nice formula that has this reasoning built in. Another way, given the same data, what you could do is you could do like a table. You could say, okay, we're going to do like males, females, smoking or non-smoking, smokers, non-smokers, total. And a lot of times you can assume a nice number for a population. Assume a population of 100, so that the numbers in the table would be percentages. So numbers in table equivalent to percentages. Right? Because percent means per century, per 100. Okay. So if we had 100 people, and we know that for what were we told? 40% are men, 60 are not. Okay, so that means we should have 40 over here and 60 over here, adding up along the row. Now, of the men, of that 40, 50% are smokers, right? So that's 20 people over here, 20 people over here. This is 50% of 40. Now, of the women, 20% are smokers. So out of the 60 women, we want 20% of 60, which is going to be 12. Which means we have 48 people over here. So you realize that the smokers in this population actually add up to 32 people. There are 32 smokers in this population. The non-smokers, therefore, are going to be 68 people who are non-smokers in this population. And of course, the population has 100 people. So we can dissect simultaneously by male versus female and smoking versus non-smoking. And now we can look at the probability. So we want the probability that if we chose a smoker, they are male, right? So this is going to be probability of male and smoker over probability of smoker. Now, male and smoker would be here. So let's put that in red, male and smoker. That is going to be here, right? And also notice that that is 50% times 40%. And then you want to divide by the probability of smokers. So the probability of smokers, well, that's just looking over here, which of course is going to be 32. But where that 32 actually came from, if you look at the table, what I did was I took 50% of 40%, and then I added that to 20% of 60%. Right? So you doing it by the table, you'll get these numbers right away, but it's actually equivalent to what happened before. So you'll notice that it's going to give you the same answer. Yeah, so that's how you can do it via table or via a tree diagram. But the thing is, I want to actually show you that we could do this via a formula. And that's what we're going to build up to today. So I'll show you how to get a formula to get this, and then I will leave you with a problem to try for tomorrow. So let's actually look at that. I'm going to give you the formula in 2 versions, and that is going to, which is unofficial. They usually don't put it in 2 versions. They usually do the last version. Okay, so now some things to note. Given a set, let B be a set, let A be some other set. Okay, I want you to recognize that for any set, I can actually compare it to another. I can write it in terms of another set in the following way. Then B is equal to the part of B that intersects with A union the part of B that does not intersect with A, which, I mean, saying that in words, it makes complete sense. If you look at, say, a Venn diagram, the set B can be split up into 2 parts. There is a part that intersects with some other set A, potentially the empty set. That's this part. But there's also a part that does not intersect with A. That's this part. So there's a part of B that's also in A, and there's a part of B that's not in A. So if I'm looking at any set B and someone gives me some other random set, this is going to be true. That set might contain some of the things in B, but it also might not. But whatever it is, I take the union and I can get that set B. So that's an important thing. Now, note, B intersect A and B intersect A complement are disjoint. You can't be in A and not be in A at the same time. Okay, so by Axiom 3, what that means is if I'm taking the probability of B, it's the same as taking the probability of B intersect A union B intersect A complement. And we know that when we have the probability of a union of non-overlapping sets, this comes down to the sum of probabilities. Someone got kicked out of just now. Oh. Okay. Now, here's what we can say after that, right? So I'm going to rewrite these in two ways. So note that probability of B given A is the probability of B and A divided by the probability of A. This means the probability of B and A can be thought of as the probability of B given A times the probability of A, right? Which I actually mentioned that earlier as well, right? I'm just rehashing that formula for you, right? So that's going to be true, that I can rewrite the probability of B and A as this product. And of course, the same sort of happens for the complement. So if I have B given A complement, that's complement, that's complement, that's complement, that's complement, that's complement. And that's the green arrow. Maybe I'll move this over there. So ultimately, I can get to the following formula. This is the probability of B given A times the probability of A, right? So what is the probability that we're in A, and then given that we're in A, that we're also in B? Plus, this is the probability of B given A complement times the probability of A complement. And ultimately, that is the probability of B. Right? Now, this is actually a very important formula. We will call it Bayes' theorem. Sometimes people call it rule, Bayes' rule. And this is version 1 unofficial. Right? So normally if you were to look up Bayes' rule, this isn't the formula that you would see. But this formula is very instrumental in deriving the formula that's usually used in Bayes' rule. So it's the conceptual leap that we needed. And so I think of it as a version of Bayes' rule. Now, here's the thing. Now, consider the probability of A given B. We know the probability of A given B is the probability of A and B over the probability of B. Now, applying the logic above, I can think of that as the probability of B given A times the probability of A over, well, now the probability of B. This is the probability of B given A times the probability of A plus the probability of B given A complement times the probability of A complement. Now, this is what people usually think of when they think of Bayes' rule. If you're a math person or you're doing statistics, you might think of this slightly differently, but let's not get into that. Because you might want to intersect it with multiple sets, not just an A, but an A, a C, D, E, F, G. And there you can generalize that formula. But this is Bayes' rule. Now, I want you to realize, so this is by version 1 is where the denominator came from. And the numerator came from by definition of probability of B given A. Okay, so that's where those come from. Now, here's what I want you to appreciate. If you're searching for a probability of A given B, but you know the probability in the opposite order, the probability of B given A, this formula is now useful. So if you go back to the original question, now you'll realize that we could do it nicely. We're given probability of male. 40%. Yeah, we're given probability of male complement. We're given the probability of, given that you're male, chances you're a smoker is 0.5, which means that the probability that given that you're male, chances you're not a smoker is also 0.5. We're also given that you're not a male, chances you're a smoker is 0.2, which means the probability given that you're not male, the chances you're not a smoker is 0.8. Now, if you look at the fact that we want the probability, given that I chose a smoker, what is the probability that it's male? Notice that the information you're given gives you a condition in the opposite order. You are given this opposite order. That's one way in which it will trigger you to think of this formula. So now we can say by Bayes' rule, the probability of male given smoker is the probability of smoker given male times the probability of male over the probability of smoker given male, probability of male, plus the probability of non-smoker given probability of smoker given not male times the probability of not being male. Right? And so now we can just go in. This is going to be 0.5 times 0.4 over, of course, that's 0.5 times 0.4. Probability of that is 0.2. Probability of not male is 0.6. And you'll notice, hey, those are all the numbers that we got the first time. Gasp. Got this last time. So this is a formula that we can use to reason through a problem that stratifies like this without the diagrams, without the tree diagrams or the tables and all that stuff. We can apply Bayes' rule, Bayes' theorem. Bayes' theorem is actually very, very super duper important. There are some philosophical differences about that. There are statisticians who don't like Bayes' rule. They like to do things otherwise. Let's not get into that. But Bayes' rule is actually very important from a conceptual standpoint, which we'll talk about later. What I want you guys to do is to try this problem over here. Which I'll leave in the notes. Spoiler alert, you can use Bayes' theorem here. But yeah, we will end there, I think. And I'll also post a second handout underneath this. Which we'll work on some problems from the second handout as well. Which I'll leave here. Probability set 2, you're going to attack problem 1. Yeah. So that's it. We've learned another formula, very super duper important formula, and try that for next class. That's it. Heading into the other class, so I will let you guys go. Thank you for your time and attention. I'll see you guys in the next one. Ciao.